Hello, it's Mrs. Scarpel, and this is the second part of Lesson 2 from Unit 1. We left off with writing recursive sequences and modeling different mathematical models for Marco's logo, which looks like an eye for his site I. He decided to experiment with making it blockier, and this is what he came up with. So now, in addition to adding on to the length, he's making everything thicker. So he's actually changing two dimensions, the length and the thickness. And you can see that happens again here with size 3. So assuming that Marco continues with the pattern as it has begun, we're going to draw the next figure, size 4, on a grid and find the number of blocks in the figure. We're also going to develop a mathematical model. We're going to do that by completing a table and writing recursive and explicit formulas. And I'll explain why we're not going to graph this one in a second. And then we're going to compare the models. So I've gone ahead and I have sketched the fourth size already, just to save some time in this video. So you'll see that size 1 has a total of 7 squares, and the thickness of each row and the thickness of the piece in the middle is 1. Then when we go to size 2, we add on each end again, and we add to the middle lengthwise, but we're also making things thicker, so everything got doubled. Then on size 3, added on yet another row, another column, and another row on the bottom, and added on to each end, as well as added on in the center. So if we look at this, my size 4 has a total of 12 squares across. It has a thickness of 4, which appears to be the pattern. The thickness in the center also became 4, and we added another row here as well as to the top. Added on each end and added on another row. Size 1 is the same in this pattern as in the original, so has 7 squares. But when we look at size 2, we now have 1, 2, 3, 4, 5, 6 in a row, and we have 4 of those rows for a total of 24, and we now have 4 in the middle for a total of 28. For number 3, we have 1, 2, 3, 4, 5, 6, 7, 8, 9 across, and we have 6 rows, so 9 times 6 is 54, but we also have 9 in the middle here for a total of 63. Size 4, we have 12 across, and we have a total of 8 rows for a total of 96, plus another 16 in the center for a total of 112. So if we look at the pattern, to go from 7 to 28, we're adding 21. 28 to 63, we add 35. 63 to 112, we add 49. And we can see that we have a second difference of 14 for each of these. So our second difference is constant. So to find how many would be in size 5, I need to add 14 to 49, and that gives me 63. And when I add 63 to 112, I have 175. And then to find the next one, I have to add 14 to the 63, and that's how we get 77. So we add 77 to the 175, and we have 252 squares. Now you can see how quickly this grew, and it's because of how quickly these numbers grew that we're not graphing this one. If we did, it would be a very narrow graph. And actually, once we get some equations here, I will show you what the graph would look like. So let's start with our recursive formula. For the recursive formula, we know that f of 1 is 7. The place where we start is 7. And then our recursive formulas always begin with f of n equals f of n minus 1. The f of n minus 1 stands for previous term, so I'm adding to the previous term to get the next. Plus, this is where the second difference comes in handy. This second difference is our rate of change for our linear pattern here. Our first difference is linear, our second distance is constant, or difference is constant. So I'm going to have 14n. And now I'm going to have to check to see if there is anything I need to add or subtract from 14n. And what I'm going to do is I'm going to take 14 times 2 and see what I have to do to it to get 21, because that's what I'm adding to get that second term. So 14 times 2 is 28, but we're adding 21 to that. So the difference between 28 and 21 is 7. So I'm actually taking away 7 to get what my total is. If I try this with 3 times 14 is 42. Subtract the 7 and I will get the 35. So this is the linear rate of change. For the quadratic. And remember, the 14 is coming from the second difference. Now for the explicit, what I want you to think about is when we have a quadratic situation like we have here, you always want to think of area or something that's being squared. So when I first looked at these shapes, I saw that I could replicate squares within the shapes. So size 1 has a total of 7 squares. I could create my own groups of squares and still have 7 groups. And I can do this as well with size 3. It'll be a 3 by 3. And I have a total of 7 of them here as well. And I can do the same thing with the 4. I can have 7 groups of 4. And all of these are the shape of a square. And if we think about finding the area of a square, it's very much like finding the area of a rectangle, length times width. It's just that our dimensions are the same. And if I look at each of these sizes, size 1, my squares are 1 by 1. Size 2, my squares are 2 by 2. Size 3 would be 3 by 3. Size 4 is 4 by 4. So we could make a very good claim that size 5 would be 5 by 5. That number we're multiplying always matches the size number. So when I write my explicit equation, I start with f of n. I know that I'm taking the side length squared, and the side length matches the size number. And I have a total of 7 of these, so my answer is 7n squared. And we can test this. I can take and put 2 in, so 2 squared is 4 times 7 does give me the 28. 4 squared is 16 times 7 is 112. So this is our explicit equation for these areas of our logos. So what can we do with what this graph is? As you can see, this is a graph that has a scale of 1, and it's going up to 10 on the x-axis, negative 10 on the y, positive 10 on the y. And you'll notice that this graph is actually very thin. The sides are very close together. Now, one thing that's different about this graph from some that we've seen, and it would even hold true for the hats, is we've only worked with the graph on the right side of this curve. We've not looked at what the graph would be on the left side. So this is a parabola. And we've been working with partial parabolas on our patterns. So we don't have any context, but we're going to describe the domain and the range and some other features of this graph. One thing I want you to remember is the domain is the set of x values. And if I look at this graph, even though it doesn't show it here, I would have arrows on here indicating that this is going to keep going forever. So really, there aren't any x values we aren't going to use. So the domain, and I'm using what's called set notation. This is not the same as an ordered pair. We use parentheses to show that there's no exact stop. And to show that it's all real numbers, it's negative infinity to infinity. The range is the set of y values. Now if I look at this graph, I don't have anything in the negative region of y. Everything is in the positive, and it starts at 0. So our range includes 0, and it goes on forever. It goes on to infinity. Now because there is a hard stop and our graph includes 0, that's why I have a bracket here. Another thing we can talk about is this graph has a minimum value. It has a lowest point. This is also called the vertex. And there we go, minimum. The minimum value is 0 at when x is 0. So I'm just going to put vertex here as well. Now another way we can describe some features is, even though this is showing that it's going up on the left, when you're describing a graph and where it's increasing and decreasing, we read it from left to right and we follow what our pencil would do. So on this graph, on the left side, it's actually decreasing. So we can say decreasing from negative infinity to 0, and I'm putting parentheses on the 0 because the 0 is our vertex. It's the point where it changes. And so once I go to the right side of the y-axis, I start increasing. So by putting the parentheses, we're saying it's decreasing all the way till it's really close to 0, and then it's increasing from 0 to positive infinity. So it's constantly going up at that point. And these are some of the things that eventually we'll be looking at in more detail. But these are some features we can have. So what are our takeaways? When we compare a linear to a quadratic, the linear is constant for a rate of change. The quadratic has a linear rate of change, which we saw in our recursive formula. For a diagram, we're only changing one dimension, so we're saying it's going to grow in length. But for quadratic, it's going to grow in length and width. It changes in 2 dimensions. In an equation, the highest power term for a linear equation is x. The highest power term in a quadratic is x squared. In the table, that's where we really see those rates of change. The first difference is constant, and in the quadratic, the second difference is constant. And the graph of a linear is a line, where the graph of a quadratic is a parabola. So this wraps up the content portion of this lesson. I'm now going to go through some retrievals, some things that should possibly be familiar to you. And here is an example of a parabola. I'm not sure what they're graphing here, but it's not the logo that we were just looking at. So the first part of the retrieval is writing an expression as the product of 2 binomials. So each expression here involves, or in your assignment, will have a positive or a negative sign between 2 items that are being multiplied. We also see that there's a matching factor. In this case, it's the 4x plus 1. So we're going to factor that out. It's like taking it to the front and writing it all by itself. And then we're taking that extra piece, or what the leftovers, I guess you could say, the 3x and the plus 2, and creating a new expression with those. What's really happening is we're doing the distributive property backwards. I have to take 4x plus 1 times the 3x, and I have to take 4x plus 1 times the 2 to get the full expansion of this, but we're just writing it as 2 binomials. So when you're practicing this in your assignment, look for what's common. In this case, it's the 4x minus 10, and you write that as the first binomial. Then you take what's left. We have 9x plus 2, and you write that as the second binomial. And that's all you need to do for rewriting these expressions as a product. Product means multiplication of 2 binomials. When it comes to finding the greatest common factor, you're looking for the largest value that will divide all of the values listed. So we have 36 and we have 45. Generally, I start with my smaller value and I list my factors. Those are numbers that divide it. So factors of 36 are 1 and 36, 2 and 18, 3 and 12, 4 and 9, and 6 times 6, but I'm only going to list it once. So of all of these numbers, which one is the largest one that divides 45? Well, we can rule out anything that's even because 45 is odd. And 3 does, but it's not the largest one. So the largest not even number that we have in this list is 9. And 9 does go into 45 5 times. So the GCF, the greatest common factor of those two numbers, is 9. For the number 8, the list isn't so long. In fact, I'm just going to write the list directly below my number 8. The factors of 8 are 1, 2, 4, and 8. Now I know 8 does go into 24 evenly, but 8 does not go into 36 evenly, so it cannot be a factor. 4, or a greatest common factor I should say. 4 does go into 24 6 times. 4 goes into 36 9 times. So the greatest common factor of 8, 24, and 36 is 4. And that concludes part 2 of lesson 2 from Unit 1.